In this video, we try to explain how to formulate IOP model for the sweatshirt mini case. So basically, we only focus on the question 1. So the sweatshirt company is a home-based company that produces and sells hand-painted. So here we know the focus is the hand-painted sweatshirts. That's a product to the children. And the forecast for next 3 periods are the 120 autumn, 350 for winter, 75 for the spring. So now let's see, we're talking about a multiple period problem. We'll assume that we let G equals to autumn, winter, and spring 3 periods. Or you can just use AWS. And then we know we can also identify multiple parameters. The first is the demand. So we know the autumn DA is 125 units. The winter is 350. DS is 75. And we also know some other parameters. For example, here we can denote the purchase cost for your item. Individual sweatshirts is $15. For example, we just use C to record the purchase cost for sweatshirt, and we use H to record the to denote the holding cost. So here they try to explain what's the holding cost. So the holding cost is the cost for facility cost, or for example electricity cost or labor cost to actually hold the item of products in the inventory. Or quite likely is holding cost also related to the interest rate, because stock normally considered as assets. So here the holding cost is 24% of your purchasing cost per year. But here we're more interested in the cost production for each period. So we just transform this holding cost into the holding cost for per quarter divided by 4, which is $0.9 per quarter. So that's holding cost. Furthermore, we also have a cost called a wage, or the labor cost. We can also use a letter capital W to denote that. Then the WG, we let WG be the wage of employee or painters. Then we know WA is $4.5 per unit. W winter is $6, and then in the spring that's $5.5 per unit. So that's basically all the costs defined and the periods identified. So furthermore, we try to also explain this situation. So this decision actually related to a linear network. So from the current start period, and then you face to 3, it's period 1, period 2. So you face to the 3 period. So that's how we sketch this multiple period really depends on your own interpretation. So here, if I define decision variable, which is the production at the beginning of each period, then we should have x1, x2, x3 located at the beginning of each period. So you could also actually use it another way. So you can also sketch 3 periods, but we only note the beginning of each period at the time boundary, then you have actually the beginning of period, you have x1, x2, x3, and then here you also have a holding cost. So the holding cost related to the inventory at each period normally is the end of each period. So if we use a second, so if we choose to use this second way to describe your production planning situation, then we're actually talking about the inventory at the beginning of each period. So it's I0, and then I1, and I2, and I3. So in this situation, we should know at the beginning of the period 1, or the autumn period, then you should actually have a inventory 0. This is normally assumption. And then I1 actually is the implied values related to your production decisions and your demands. So in the first situation, you actually also have I0, I1, I2, I3. So this doesn't matter how you actually sketch this situation, but here we're mainly talking about once you decided the production quantity, you also know the demand in each period, you actually can calculate the inventory. So this actually called the balanced demand constraint. We see the constraint later. So now we know we would like to make decisions about decision quantities. Then we define, so we can do that. First step, we define decision variables. We let xg or g equals to AWS, so xg be the production quantity in period g. So g equals to AWS, and let ig be the inventory quantity at the end of each period. So now we're done with the first step. We identify the parameters. We also define the decision variables. So next step, now we can actually try to formulate the objective function. So now let's try to define the objective function. So you can choose the second step, write down the objective, define or formulate the objective function. So first we face to a decision problem to minimize the production and the inventory cost. So your objective function is to minimize first the production cost. Production cost, we know the production time for each unit is 1.5 hours. Then you should times your production quantity. So your production quantity is x1, x2, x3, or xa, xw, and xs. But the salary is different. So for the autumn period, you have $4.5 per unit times x autumn, and then plus 1.5 times $6 times x winter, plus 1.5 times $5.5 times x spring. So that's basically production cost. We also have inventory cost. So we just directly write down the inventory quantity times the inventory cost. So here we have calculated the inventory cost is $0.9 per period. So here we just directly write, change color. So 0.9 times IA plus IW plus IS. So this is an extended form of the objective function. You can also write them as a compact format. So you can just write minimum sigma g 1.5 times wg, which are the wages, times the xg, and plus the holding cost h times sigma ig. But this is not required, so if you can write the extended form, that's totally fine. It's only because if the problem is large, you actually have a lot of items to write down, so use a compact form will be more efficient. So now we have objective function, so we just try to just move it around, get some space for the constraints. So in this example, so second step, let me see, you have the same kind. So third step, we actually formulate the constraints. So first, let's see, the main constraints are the demand constraints. So we try to produce certain quantities in order to satisfy the demand. So of course, the optimal solution is to produce the quantity which not give extra inventory at the end of the selling season. And then we also know at the beginning of the selling season the inventory is 0, so we can actually gradually write that from period to period. So first, let's say in the first period we have the we have the production quantity is x1, and your inventory at the beginning of this inventory in this period is the I0. I0 actually equals to 0. Then we can just write this I0 as a 0. So I just wipe it. So now we just write x1 plus 0 equals to, so the purpose is to satisfy the demand. I will just write XA, the demand in the autumn. But if you cannot sell, this quantity is allowed because you have actually cheaper cost in the autumn. You could actually produce more and hold the inventory to sell them in the winter, because the winter the employee or labor cost is relatively high. So you can actually produce more than you need in this period. So we actually also allow you have a positive inventory at the end of autumn. So you can see you get these constraints. So your production quantity plus inventory equals to demand plus the end of period inventory. And then we can continue to write in the winter, you have the same situation, produce XW plus the inventory from the autumn period equals to satisfy the demand in the winter period plus extra inventory in the winter period. And similarly, for the spring semester, you produce XS plus the winter inventory should be used to satisfy the demand in the spring. And also we assume that the entire planning horizon, so in the end you should actually hold inventory of 0, because any extra inventory will not bring revenue, will just cause extra costs to hold it. So that's basically the main constraint. Here we also know the x, g, I, g, they're all non-negative. Negativity in constraints. So if you understand the formulation, so you can just put this problem into its model in the Excel solver to solve that. Uh, so at this stage, it's more important you are able to formulate the problem. You will get the Excel solution, so you can follow how to solve this problem in Excel. So this video will just stop here.